Ever wonder what a tree looks like from the hallway? Only the rightmost nodes peeking out? Binary tree right side view, Pattern Mastery 100 is a quick litmus test for your BFS/DFS instincts. Bong interviewers love it because one clean pass nails it in ON, and the explanation shows you can tame levels and visibility like a pro. Let's crush it with basics. We're given a binary tree. From the right side, at each depth we only see the rightmost node. Return a list of those node values from top to bottom. 2 clean patterns. BFS by level, Q. The last node we pop for a level is the one that's visible. DFS, right first, pre-order. The first node we hit at each depth is visible. Both are ON time, OW space, W equals tree width. We'll do BFS. It maps perfectly to one value per level. Plan with BFS. If root is none, return. Push root to a queue. While queue not empty. Record current size equals len queue. Iterate that many nodes. In queue children. The last node in this loop is the right side value for the level. Append it. We begin with a solution class. This acts as the wrapper for our entire algorithm that will compute the right side view of a binary tree. This method, right side view, takes the root of a binary tree and returns a list of integers representing the nodes you would see if you looked at the tree from the right side. We create an empty list called res. This will store the final right side view values, one per tree level. If the root is null, the tree is empty. There's nothing to see, so we just return the empty list. Next, we create a queue called queue. This queue will help us perform a level order traversal, also known as breadth first search, BFS, perfect for visiting nodes level by level. We place the root node into the queue to kick off the BFS process. This loop runs as long as there are nodes left to process in the queue. Each cycle of the loop handles exactly one level of the tree. Time complexity note, BFS processes every node exactly once, making this loop ON for a tree with n nodes. Here we capture the number of nodes in the current level. Since BFS stores an entire level at a time in the queue, queue.size tells us how many nodes we should process before moving to the next level. This inner loop processes each node in the current level. The variable I tracks which node we're on within the level. We remove, pull, the next node from the queue. This is the node we're currently visiting. This is the key insight of the right side view approach. The last node we process at each level, the one with index I equals level size, 1, is the node visible from the right side. So we add its value to the result list. Think of it like looking down a hallway. At each depth, the far right object is the only one you can see. If this node has a left child, we add that child into the queue. It'll become part of the next level's processing. Similarly, if the node has a right child, we add that to the queue as well. BFS always expands children from left to right, but we only select the rightmost node at each level. This ends the inner loop. We've processed the entire level. This closes the BFS loop. Once the queue empties, we visited the whole tree. Finally, we return the list containing the rightmost value from each level, the exact right side view of the tree. This closes the right side view method. And that closes the entire solution class. And that's how this algorithm works. It first sets up a queue to perform a clean level by level traversal, then picks out the last node from each layer to build the right side view. Efficient, simple, and elegant. Test case check. Let's walk through it. Input root equals 1, 2, 3, null, 5, null, 4. Let's test our function using this tree input. 1, 2, 3, null, 5, null, 4. This array represents a binary tree in level order form. 1 is the root, 2 is the left child, and 3 is the right child. 2 has a right child 5, left is null. 3 has a right child 4, left is null. We're looking for the right side view, the nodes you would see if you stood on the right side of the tree and looked inward. Quick logic check. From the right side. At level 1, you see 1. At level 2, between 2 and 3, the visible one is 3. At level 3, between 5 and 4, the visible one is 4. So the rightmost values per level are 1, 3, 4. Output 1, 3, 4, and that's exactly what our program returns. 1, 3, 4. It matches the expected output perfectly, which shows the logic is spot on. So, our implementation is correct. The algorithm cleanly captures the rightmost node at each level, producing an accurate right-side view of the tree. We start by importing the Java utility library. This lets us use helpful classes like list and ArrayList. This declares a class named solution, which will hold our method for computing the right-side view of a binary tree. Here we define the method right-side view. This is the function someone calls to get all the values visible from the right side of the tree. We create a list called raise, which will store the answer, the nodes you would see if you stood on the right side and looked at the tree. This line starts a recursive depth-first search from the root, beginning at depth 0. Because each node is visited once, the DFS runs in on time. After the DFS finishes exploring everything, we return the final list of visible nodes. This closes the main method. Now we define the DFS helper. This function travels down the tree, keeping track of how deep we are and collecting the first node we see at every depth level. If we hit a null node, that branch ends. We stop exploring and return immediately. This prevents unnecessary work and keeps the recursion efficient. This line is the clever part. If the current depth matches the size of Res, it means we're visiting this depth for the first time. And because we're visiting the right side first, this node is the node visible from the right. So we add this node's value to the result. We continue downward by exploring the right subtree first. This ensures the very first node we encounter at a new depth is the one visible from the right side. And then we explore the left subtree. Any left side nodes at this same depth come after the right side and are therefore not visible from that right side perspective. Closing the DFS helper method. And closing the entire solution class. And that's how this algorithm works. It first creates a list to store the answer, then uses a write first DFS to capture the first node at every depth. Efficient, simple, and elegant. Let's test our function using this input. 1, null, 3. These values represent a binary tree where 1 is the root, there is no left child, and 3 is the right child. Here's why the solution works. Our algorithm traverses the tree and collects the node values in the required order. For this structure, it first visits the root, 1, then moves to the right child, 3, and since there's no left subtree, the sequence is simple and direct. And that's exactly what our program outputs. 1, 3. This matches the expected result, confirming that our traversal and value collection logic is behaving exactly as intended. So, our implementation is correct. The algorithm successfully extracts the node values in order, efficient, accurate, and reliable. The key takeaway? When working with trees, clarity often comes from thinking in levels. Mastering BFS helps you not just see what's in the tree, but what's visible from every perspective. Let's wrap it up. The binary tree right-side view problem is one of those interview favorites that tests your mastery of BFS, DFS, and tree visibility logic. It's a clean challenge that reveals how well you understand level order traversal, and whether you can capture exactly what's visible from the right side in just one efficient pass. We're given a binary tree and asked to return the values of the nodes that are visible from the right side, one per level, from top to bottom. There are two clean approaches. You can use BFS, where the last node you see in each level is the visible one, or DFS, where the first node you visit at each depth, going right first, becomes the answer. Both take on time, but BFS naturally fits the idea of one value per level. We built a BFS loop using a queue. For every level, we processed all its nodes, tracked their children, and recorded the last node of that level as the one visible from the right. That gives us one clear value per depth, no duplicates, no confusion. We ran this in LeetCode, and it worked exactly as planned, efficient, one clean pass through the tree, no runtime errors. The solution passed all test cases, confirming that it correctly captures the rightmost nodes while staying within ON time and OW space complexity.